Oh, good. Okay. Who's hungry? I'm hungry. So let's, it's supposed to increase your concentration, maybe. So I won't finish early, I'll tell you right now. Never have in my life. So I'm not going to start today finishing our talks early, but there might be some surprises. All right. So I just want to say that robot learning is an old problem. So, I'm probably the oldest person in this room. This is increasingly starting to happen. And, I actually, in preparing for this talk, I looked up an old paper that I have with my former advisor, Rod Brooks, from 1993, which was right before I finished my PhD. I finished in 94. It's called Real Robots and Real Learning Problems. And I couldn't find a copy of it, but I know it's in a bound volume in my office. Otherwise, you have to pay Springer to read it, which I recommend that you do. Because apparently it's getting citations, whatever. But look what we said in the abstract in 93. The weakness of existing learning technologies and the variety of knowledge necessary to make a robot perform efficiently in the real world suggests that many concurrent, complementary, and redundant learning methods are necessary. You know what? I stand by that 30 years later. There's nothing that you would have heard in today's talks that makes that untrue. You might have heard stories about how it's all different now and how these foundation models are going to solve it all, but we old geezers, we're going to tell you it's not true, and then later we'll be right. But then you'll be old and you'll be saying to the younger people, it's not true. Because really, I mean, if nothing else, look at biology. There's no way that there's a single methodology that is solving the reality of efficient, safe behavior, goal-driven behavior in the physical world. Not happening. So let's talk more about that. But that's just to get you riled up. It's not going to be it's not just more data. It's not. But yes, it's AI. Oh my God, I hadn't noticed. Yes, so this is happening and it's really important. But what is more important is to understand what intelligence really is. And so intelligence, biological intelligence, most biological intelligence is physical, social, and cognitive. And so the world we're in right now, the large majority of people, including people in big tech and small tech, are all obsessed with the cognitive, right? Cognitive, that's all it is. It's, mostly language, but kind of expanding to multimodal, but not really multimodal people because there are no forces, there's no real haptics, nah. So it's not really multimodal. And people are understanding in robotics that of course we need physical, we'll get there, but still the belief is it's mostly cognitive. And this is where this whole idea is like, oh my gosh, we now have these large foundation models and they're somehow going to leapfrog robotics. We'll see. But the part that everyone is also forgetting massively is that there's also social. Social intelligence is a different kind of intelligence. It is not just physical. Well, I think that's obvious, but it's definitely not just cognitive either. And a lot of people in the larger field of tech will tell you that social fits under cognitive. They are wrong. And that is because social behavior is one of the oldest in terms of evolution. That drove the evolution of human intelligence. And it is profoundly embodied and profoundly physical. And the reason that I want to talk about that today is not because we're going to talk about social robotics today. In fact, we're not. We'll touch a little bit on socially assistive robotics, but mostly that's not what I'm talking about. What I'm really wanting to focus on is that, in fact, amazingly, you may not believe it, but you will not get really good physical behavior of robots in this world, in this physical world, without some social intelligence. Shocking, yet true. Because it is precisely that social intelligence that drove all of our intelligence, including our physical interactions. So it's just important. Yes, so human intelligence, and that's where we're going, right? AGI and beyond. It really does emerge out of a context of embodied and situated interactions, right? You got to have a physical body and you got to be situated in some environment. And you can't abstract that away, and you cannot do grid worlds. And you cannot do 2D, 3D, or ND simulations. It ain't real. So it doesn't mean you cannot bootstrap things with simulation. Don't get me to say that, although my former advisor might be saying that, and he might just still have a point. So simulations are doomed to succeed. You cannot, they won't take you all the way. So you got to get that real symphony of physical, cognitive, and social. And we'll talk about that. So, but again, just don't forget, the social bit is what really made us as smart as we are. So things that don't move are not very smart because they don't have to deal with as complex of a physical world. Once they start moving, they get smarter, but they're not really smart until they become social. It's really important. And not just for social interaction, but for reasoning. And they really are all necessary. And so that's the point I want to make. And I'm going to keep making it. Okay, here's some cool facts from biology / physiology, neuroscience, and so on. And they basically are going to get to some things that are very related to how we are currently training models and using models and how we think models will solve all of our problems. Okay, so first of all, there are lots of old studies, like older than me, that show that if you take animals, and this was done in rats and kittens, you can't do it with people, it's not humane. Animals cannot learn skills from observation, not because they're dumb, we couldn't either. You got to move your body. So, simple experiments like you bind rats' legs and you show them a maze and they can't learn it, you let their legs just move without actually traversing the maze. Just move the legs as you are flying them over the maze, not in a drone, and then they can learn it. So why do you have to move your body in order to learn the layout of a map? Because fundamentally, the way we're wired, we learn spatial things by moving our body. And in fact, the thing that I love to always bring up is like, when I'm doing this, all your brains are ready physically to imitate. You're just suppressing it. And there's some people who have deficits who actually would not be suppressed, and they would be doing the same thing. But your body is constantly imitating, and that's, by the way, how you know that what I am doing is flapping my arms. Is your physical imitation system is mapping to your, we'll talk about it in detail, but like not here, mirror neurons in order to basically classify this behavior. That's how you understand it. It's not your high-level cognition saying, oh, that's called flying because I learned that from language. No, it comes from the motor system. So the next thing is humans also can't learn from screens. And we know this from babies because, again, you cannot do inhumane experiments with humans. But we do know that you can show babies all kinds of visual images, and people do now. They show them iPads like at birth. And kids, the visual cortex, the auditory cortex is lit up, things are firing. But if you actually do testing, they haven't retained it. They can't retain it from a screen because that's not how we're wired. And also, by the way, swiping is not enough motor learning for a baby. There really are. I just was listening to this and reading about it. More screen time is correlated with many developmental disorders. Surprise. We're supposed to be in this physical world and learning from it. The other thing is social delays. So it turns out that if children are not exposed to social interactions in the physical world, which unfortunately got massively tested on a global scale around the pandemic, as well as covering facial expressions, then they have developmental delays. And those delays are not just social, they're cognitive and also physical, which is just more and more evidence from deficit to show that these things are all tightly connected. Yeah, I talked about this imitation and body maps, right? So we already talked about it. So like when we think about demonstrating something to a robot without it having enough physical control to map onto, if you're just demonstrating in order to map to language, again, you're not getting the deep binding that's going to allow you to generalize and truly learn. And then finally, more interesting stuff. When humans are learning new skills or relearning through rehabilitation, if they don't have the drive to actually do this, they can't recover or they can't learn. So you can take passive learning. You can take humans and show them a bunch of things and, put them through, which is teleop, by the way. You can teleop people. But if they don't want to make the movement, they're not, even though you're making the movement for them, they're not recovering physically. So there's something really profound about motivation that drives the movement. So you have to try to move, even if you physically cannot. If you're not trying and someone's just moving your arm, you're not actually able to learn or recover. Again, why am I bringing this up? Isn't this a fun list? This list does have a point. It all speaks to the profound intermingling of the function of the way we're wired, of the cognitive, physical, and social. And in fact, in the other order. Physical first, then social, and then cognitive. These things work together. When you try to create artificial systems that ignore some of these parts, they don't work. So this is why I'll always say, and I think we all agree at RSS, that there's no AGI without the physical part. But guess what? You've forgotten the social. You need all three. So yes, AGI, it has to be embodied. It's not going to be able, look at how bad these models are about spatial reasoning. And you can shove in a bunch, you can fine tune it with a bunch of spatial stuff, but it's not enough. There's always more stuff they won't know because they have no grounding in the physicality of embodiment. Now, they're maybe going to get it, but they have to get it from the right kind of physical data. And that is where we're not doing it well right now. So I'll talk more about that. And then the social bit is completely overlooked. So the vast majority of data being pumped into foundation models are not interactive data between robots and people and multiple robots and actual physical forces and things like that. That's what you need. And we don't have it. We're just not doing it. It's hard, it's expensive. We're doing other things that are expensive, but we're choosing not to do these really important things. So I've been in robotics for a long time. And I looked back because I thought it was fun to do for this talk. I looked back at all the learning that we've done. This is not a complete list. My first work for my master's thesis was learning navigation. So it was early SLAM, really. And SLAM, if anything, is kind of like the most sort of solved robotics problem. Simultaneous learning and simultaneous navigation and mapping, right? And so I did that early on, and it was based on rats, place cells, how rats navigate. So I guess I've always been grounded in biology, which turns out to be helpful. Then moved to multi-robot stuff. Then moved to humanoids. This was all now with grad students. And then now we're here. It's a lot of different things. What is it? Attention deficit? I would say no. It's fundamentally, well, the first thing is you get amazing students, you let them do stuff they're really interested in. But in the end, what do these things have in common? They have in common the synergy of the three aspects that I just talked about. Even though we discovered social 25 years ago, which is still a long time ago. First of all, perception. So, most of robotics still today, oh my God, we're going to figure out the state we're in. Not gonna. Okay, so what's going on? Perception is really a continuous process, right? So you need this you're in complex real world environments, and you have a multitude of models. It's not just one model. And I'll talk about some work that has been going on in our lab to really get to that. So back before foundation models, we were coming up with clever representations. Representation, never heard of that? That's kind of gone away because now we just have the one representation, which is embeddings. But people used to think about this, and it's not a problem that's gone away because the human brain uses various kinds of representations for different kinds of data. We even have different structures in the brain. There's a reason for that. I'm not saying that we have to rebuild human brains, but when we look at the limitations that our models have, we might want to learn from biology. So I think the problem of perception, we like to think now, well, vision models are pretty good, but they're really not. They're way better than they were 4 years ago, but they're really not that grounded in spatial reasoning or anything like that. So it's still a really hard problem. And then interaction, I think, is everything, right? So the reason that our brains are as sophisticated as they are is not because they can figure out what state we're in and then have a policy to tell us what the next thing, the action is that I should take to move to the next state. No, it's because they're actually able to continually predict what is likely to happen next. So your brain is not a policy that decides how you should act. Your brain is a predictor of what is going to happen. And it's a really biased predictor, and it can often be wrong. And this is a super fun thing you can experiment on your own about. But there's this continuous stuff where there's kind of a serve and return relationship with the world. Serve and return is a thing that from early child development where like a parent does something and the child is supposed to do something in return. And then the parent automatically does something like smiles or leans in. These are fundamental for learning this dynamic, which is then all of your perception. All of the perception is like, I'm talking, some people are nodding, I'm nodding back, like I'm engaging. Everything is a dynamic. There's no static state. There's no static policy, right? So that's really important to think about interaction dynamics rather than kind of thinking about converging to a policy, which is still an issue, right? In robotics and in HRI. And then communication. If we're going to talk about people, people are constantly communicating. We're communication machines. I'm talking, I'm a big talker. But even when I'm not talking, I'm constantly communicating. I'm communicating with my body pose. I'm communicating with my eye gaze. I'm communicating with everything. I can't help it because that's how humans are. And that's how actually animals are like that too. Like, rabbits don't make any sounds. Did you know that? That's so cute. They make no sounds, but they will tap their foot down when they're frustrated. Super cute also. Lots of YouTube videos you can check out. So there's always communication. Some of it is intentional, some of it is not. There's some amazing signals there, foreshadowing to Nathan's work, that we're not using because we're so obsessed with teleoping things intentionally. Yeah, so there's a lot of communication that is happening that's coming from people that we could be using in training models. So we love to work in socially assisted robotics because I like to think in our lab, we really are about helping people. But it really is a great challenge for ML, and I'll talk about why that is. ML, robot learning. I couldn't put RL because then you think reinforcement learning, and that's not what I mean. I want to talk about social. So I'm going to talk a couple of bits of old work and then a lot of newer stuff. I'll talk about dynamics, right? So some early work we did, well, early, I don't know, several years ago, Lauren Klein, looking at deep learning models for perception to predict where an adult, but turns out also a baby, might look in order to move the robot so that we can do the most surprising action, the most salient action that the baby would then look at because they're sort of wired to imitate. So it's this dynamic, it's this serve and return. The robot is going to predict where the baby will most like to look. It will make an action to drive baby's attention intentionally to that place. The baby will then imitate. The robot will then drive that action by making it like stronger, so make the baby kick harder. This is a dynamic. This is a time series, basically a complex system that you're trying to drive. So what I'm trying to get across is this is so different from like a simple policy, because it's not a policy because you cannot fully figure out the baby's state at any point, trust me, or what the baby's going to do next. There's some finite set of states, like Lauren reduced it down to like playful, happy, crying, asleep. And we can sort of do that, except half the time between crying and playful, it's actually very difficult to tell. And it's really not just 3 states. So on the one hand, you can reduce the state space in a clever way to create something, but really what's happening is this really ongoing dynamic, which is very rich. Now, speaking of dynamics, we're looking at groups of people interacting and having the robot mediate. And it's one, because support groups are an important thing to help people with, but also it's a really, really interesting hard learning problem. You have to understand the back channeling, right? So if I want the group to maximize disclosure, I want everyone to relax, I want everyone to say really emotional things about themselves, and I want everyone to feel better at the end. How would we do that without telling people what to do? Because when you tell people what to do, they do the opposite. So that's not a good strategy, right? So we know this from behavioral science, from behavioral economics in particular. So how do we get implicit goals? How do we achieve them? By controlling behavioral dynamics. And I think this is just, you could do single party, multi-party, pairwise. But what I think is fundamental here is that these dynamics are where the rich data come from. And then whenever you create models which do not have such rich data, and then you test them on really simple things like, oh, let's build another desk from IKEA, which no one's actually ever done truly. And then you put them in a real world scenario, then they fail, because that's not what the real world is like. So what I'm driving at is you need these dynamic scenarios to collect data from. Another dynamic scenario that we're dealing with is actually helping students deal with anxiety. How is this robotics? It is robotics, because when the robot isn't there, their stress levels and their psychiatric distress are not reduced, and their alignment with the chatbot is really low. So you can have all the chatbots in the world you want, and people will engage with them, but they will not actually feel better. So now the robot is important. What should it do? How should it move? These are all really important open questions that we're going to get to test in a massive randomized control trial. And massive RCTs do not lend themselves to trying many things, unfortunately. But what I'm trying to say is having a robot that is this simple, that has very few affordances for expressivity and action, is still a very large space for creating real-time dynamics where the user can be looking at the robot, looking away, turning their head down, and the robot can use its few affordances. And now you have a dynamic, and this is hard. It's already really hard. So I think when people obsess over unscrewing things and, you know, these like fine motor behaviors, and they can't do anything in this area, I think it's important to understand where these dynamics come from. We've done a lot of work over the past 25 years in autism. I want to push this forward because one of my messages to you is to stop working in clean domains and go and just work in messy domains. Because it's like working on a really hard problem. If you make any progress in a hard problem, it's going to help a lot the really easy problems, which most other people are working on. So autism is an amazing domain because every user is different. Every user changes over time, even within a single session. So you cannot apply any of the standard stuff. And so that's really driven a lot of interesting research in the lab. Simple things like, how can I even tell if the child is engaged with the robot? Multimodality helps, sure, but it's not enough. There are no models that you can apply because each individual really is very non-stationary. So then, you can do things like you can use data from others, but that doesn't work because one, there are not a lot of data, and two, the data are a mess, and three, each individual is different. Or you can do just models of the individual. Well, that turns out to be hard because you only know so much about each individual, so you're not very powerful. So you want some combination of this. Why do I bring this up? Because to the extent that we are sitting here and waiting for these models that get ever bigger to resolve these issues, they're not going to. I'm just going to put my foot down right now and tell you that there's never going to be a model that's going to be fantastic at determining interactions with a child with autism. Because there's never going to be a model where that is, I mean, you can fine tune it, but still, there's too much, for the same reasons that we have problems now. There's just too much variance in the data. So you're always going to need some specialized smaller models. What does that mean? That means that very likely for the foreseeable future, and I mean very long term, we're going to need combinations of models. We're going to need hybrid methods. Nobody likes hybrid methods. They're so messy. They're not principled, blah, blah, blah. Your brain is very hybrid. Okay, for hard problems, we need hybrid methods. So I think, again, not to beat a dead horse, but the obsession with just thinking that with a ton of data, one model to rule them all, no reason to believe that. I had this discussion actually with Dario Amodei last year, and I was so pleased that he said the same thing. He's like, yeah, I don't really think these models are ever going to be good enough to work on those kinds of problems. And I was like, oh, I like you. You're smart. Because pretty much all the other CEOs from all the other big companies will say, oh, yes, of course, Model X. Well, maybe not today, but very soon it will do everything. It will not. So go Dario. And then, oh yeah, just to get back to kids with autism. Okay, so even just after we figure out sort of maybe what's happening and maybe they're paying attention and now you want to help them, there's so many levels of adaptation because it's an interaction, right? So yeah, you want to help them with the content you're providing, which you can call the task. Sure, but you also have to deal with the feedback you're giving them and the levels of feedback and personalizing the feedback. There's just a lot going on. And that's the reason why, for example, helping someone's learning process is not a trivial problem. And people have had intelligent tutors for many decades, and guess what? They're far from being enough. So these are really hard, heterogeneous learning problems. We're also doing some stuff in speech. Just to say, it's another example where neither a generic model nor a fine-tuned model is actually good at helping a kid with atypical speech actually improve their speech. And so, yes, you can do test time adaptation, and that's one of the things that Zhonghao Shi is doing in my lab. But just to say, there are going to be a bunch of models, small and heterogeneous, that are going to be required for non-trivial tasks. Oh, and let's return to robotics, because I know you care. So Zhonghao and others, including Nathan here, curated a kind of a benchmark to see how good these vision language models are for robotics. And of course, not surprisingly to us, but we are biased, these models, even the fine-tuned ones, are really terrible at multimodal cues, at eye gaze, at ambiguous language visual instructions. I know we just had a conversation here about, oh, it opened the oven, but not the drawer. But these are just stories. These are one-offs, two-offs. In general, when you run a benchmark, you find that these models are terrible. They're terrible at spatial reasoning. If you take a simple spatial reasoning intelligence test that is given to children to determine whether they're ready for a certain level of school or whether they need special support, models are terrible at that. So when these people are waving AGI flags at you, just give them a simple test. Of course, realize that they're then fine-tuned on the tests. So, give them a picture that you drew. Doesn't work. But it's important to run these benchmarks. Oh, this is Nathan's work. Again, back to my point earlier about how training data come from interesting places and really sort of people are not thinking broadly enough. The thing that I like about Nathan's work, which is possibly not what he would like me to say, but that's always the case with me and my students. I like the idea that basically as users perform exploratory actions, there's a lot of information there. There's information in what they look at, and there's information in what they don't look at. And taking advantage of that, rather than establishing this very deterministic, I will tally up you and I will tell you what matters. And well, that's not how it works, because that's not how humans operate. So if you really want to learn from demonstration or from demonstration, then you need to look at all of these other signals that are coming, right? The gesture, where they look, where they don't look, what they choose, and so on. So Nathan has this, I'm not even going to let him talk about it because we're running out of time, but really cool work where you're basically the exploratory actions people take, which you would think in a basic approach, let's ignore those and just look at the ones that are focused. Well, no, there's a lot of information there that even in the end saves you data. Nathan, say it in 3 seconds.
So the idea sounds like when you're trying to optimize for someone's preference, you like create trajectories that like switch over the whole space. And we kind of use CMAES to restrict the search space so that you get better suggestions to the person, and you can like explore these large representation spaces more easily, and that are like not super semantic.
So again, engage the user. Talk to the person during the learning process, not in some kind of like, I will give you rules and then you can go off. So again, it's this dynamic, which is so missing in most of machine learning. Oh, this is very cool, but I'm not going to show it. You need to talk to Nathan. Nathan just graduated and is doing a postdoc shortly, and he has many things to show you. I thought this was so funny. This is such, like, who talks like that when they're interacting with the robot? And yet there's so much ascribing of intentionality and so on. And that is, again, to get to like the rich interactions. Like when engineers provide data for robots, that is not how real people interact with robots. So it's really quite irrelevant what you train your robots on by engineers or Turkers or all of that, because the real world interactions are nothing like that. And that's been shown for so many years, like back when Sawyer and Baxter were new robots and they were put in factories and everybody expected factory workers to operate one way and they behaved totally differently. They're like, oh, but I want to know what it's going to do. And can you tell me a joke? And then they added eyes on the screen, but they didn't think of doing that before, which is kind of obvious to HRI people. So what I'm saying is fundamentally for these foundation models, they're not getting the right data. So they're not going to get as smart as they should be. This is in here because I'm going to tell you to be brave. And that's going to be one of my parting words in the last 2 slides. Don't worry. This is brave. This is brave research. I'm very proud of Nathan. And I'm proud of students who work on autism, work on depression, comb hair, do brave stuff, because then you're going to find really interesting problems. There's no problem that's too narrow if it's a real problem in the real world. Why are we doing this? We're doing this because people post-stroke and post other brain issues or dementia, et cetera, cannot actually groom themselves, which is a real sort of just a fundamental issue of feeling good about yourself. So yeah, it is an assistive task. Assistive tasks are great. They're really hard because it's hard to actually help a human. Whereas helping a robot is pretty trivial. Just do whatever it is that he can't do, which is most things. But helping a human is really hard. And I highly recommend that people work in assistive because determining what the human needs in real time is really hard. And most humans are terrible at it. Most humans are terrible assistive unless they really care about the person, because we tend to badger, we tend to presume, we tend to basically pander, we tend to assume that people are less capable than they are. We do this all the time. So no wonder robots are even worse at it. But if you think about assistive as a domain, you will see a great many challenges and a great many opportunities for collecting data. You don't have to do hair, although I think hair cutting next. So closing up, 2 last slides. I find this intersection of HRI, sure. We know we need HRI in order, so we've all agreed that we need human-robot interaction in order to get data from humans, okay? Yes. Although to the extent that people are not doing that, it's silly, but okay, we need that. But it's more than that. We need the behavior that the humans are doing to be truly motivated, which is why I like socially assisted robotics as a context. Because the thing that the human is doing is usually really challenging for them. It's high stakes. And so they're motivated to do what they're doing. And then you're getting good data. You're getting meaningful data. You're getting these interaction dynamics that are in some sense creating a flywheel. And I think that's really interesting. And it's interesting for many types of learning because there really are, I could think of it as 3. There's kind of learning new skills where you're demonstrating something to the robot, maybe how it should brush your hair. You need it to adapt to changes over time. I don't know, you got a haircut. And then there's personalization. This is how I want you to do it. This is how I prefer it. I prefer that you start from this side, or I prefer blah, blah, blah. These are different types of learning, very different for each individual, all dynamics. Right? Why would we think that this will all just fall out of some big ass model? I don't know. I don't see it. Okay, so Get out of the lab. So my well-meaning advice to you, I know advice doesn't really work, but for those who, for the three people who care, get out of the lab. You're going to get interesting problems for free, literally for free. I cannot stand it when people say, I don't know what to work on. Really? Wow. Get out of the lab and go somewhere where people need actual help, which is likely not where you live, but maybe a little farther out. So real world problems. Get humans in the loop and don't test with your lab mates because lab mates are your friends. They are completely unintentionally, subconsciously helping you. Okay, unless they really hate you, which is something you should look into. But you know, it's not real data. It's just not real data. Also, Turkers, all of that, not real data, because these people are motivated to finish the task as quickly as possible to maximize their income. That is not interaction. You got to think about, you need high stakes interactions, which is why a system is great. So that people are actually engaging in a dynamic where you're collecting real data. By the way, you know, I know we all write papers that say beautiful stories, but just remember you're telling stories. Actually, you're selling stories. So whenever you have a nice story or a bunch of papers coming out in 1 year, you're probably not saying that much. I'm not telling you not to publish. You got to publish. There's a world out there. But just be honest with yourself about how meaningful this stuff is and work on hard stuff. Be brave. Hard problems, atypical approaches. You know what? I'm here to tell you it works out. I always did the fringe stuff, always, and it paid off. So, and also, when you do all of that, I think this is probably the most important message. Think a little about humanity and the world and what we're doing to it right now. And we're doing some serious stuff to the world. So try to work on stuff that enhances human ability and doesn't replace it. And it doesn't take away human purpose. You're literally shaping the future. Think about that. Don't just do stuff because that's what your advisor does, or that's where there's a data set on the web, or that whatever. Don't follow the crowd. Think about meaningful stuff and think about its impact downstream. Thanks to all my students. All right, stop.
Maybe take one.
Yeah, and I can go outside and talk to anybody. I have a promise to answer all questions that people ask me in person. Yes.
Yes. I'm gonna say, I was thinking before, this is the most fun and clever way to express what you said. But then I said, I'm not gonna say that.
But you did. Okay, well done, well done.
That's
Yeah.
But I'm not gonna say it because probably I'm biased because I'm subscribing to everything you said, except your objections. But I'm gonna offer you one.
Okay.
When you talked about the intelligence, I tend to agree with what you said, but
Yeah.
In terms of social intelligence,
Yeah.
I still need myself more time to
Okay.
really agree on that, because we can imagine we are in the bubble of social, very social animals, and we tend to see through that lenses, right? But we can experiment thoughts, like, for example, we can stretch the autism, for example, or just give an example of Newton, for example, was said to be a very antisocial.
Tesla is a better example.
Yeah, but you know what I'm getting, right?
But you cannot ask that question. So I have an answer for that, which actually was earlier on my slide, but I should have said it. You cannot take Newton or Tesla or any human because the human was developed in a social context. No, but no human can be taken as an example because humans are developed in a social context. So unless you talk about feral humans raised by wolves, which by the way, doesn't work. That's not a thing. You know, people love telling those stories. Those children don't survive or perhaps become a wolf, but they're not human. They don't have human level intelligence. Okay. So the social development of a human is fundamental. But the question you can fairly ask, so no, you cannot separate the social from human intelligence. It is social from day one. You cannot isolate humans and take development out of it. Development is all about interactions with other humans. So it doesn't work. But you could say, well, maybe we don't care. I mean, after all, we're trying to create super intelligence. Why does it have to be human? And I'm going to say it has to be human-like because it has to interact with us. We're doing this for us. We're not playing God. If you're playing God, you know, grow up. Okay? You're not trying to play God. You're trying to create systems that will help humanity. Therefore, they have to interact with humans. And that's why we need to understand human social intelligence. But in terms of pure intelligence, you cannot talk about human intelligence without the social part.